Thank you once again for coming. I know you had very exciting choices that you could have indulged yourself elsewhere. The fact that you're spending time with us really means a great deal to all of us. In this session, we will be talking about how Dream11 has leveraged AWS to enhance experience of something that is very, very passionate for any Indian, which is game of cricket. Good afternoon, my name is Satinder Singh, and I head the solution architect team for AWS in India. Srijan, why don't you introduce?
Good afternoon, my name is Srijan Gupta. I work as VP of Engineering in Dream11.
Hello everyone, I am Rachita Chaudhary. I am also VP of Engineering with Dream11.
Okay, before we get into tech scale, I think it's important that we understand some of the contributing factors that are leading to the scale that we will be talking about. The first one is, if you just look at India, we're a fairly young nation. Almost 65% of our population is below 35 years of age. The second factor is internet penetration. We are a large country, almost 1.3 billion people, but 900 million of us have internet access. And the third factor is just the cost of data. India is leading as far as affordability of the data is concerned. And in the recently concluded India conference, our Prime Minister said that it is 12 cents per GB. So it's really large amount of population, fairly young, and having access to cheap data is creating the environment that we will be talking about. Add that to cricket. And while India has evolved, cricket, as I said, is almost like a second religion, but cricket has evolved also a lot. And the early stages of cricket, by the way, it's still being played. The match is played for 5 days. The longest that it has ever been played is 9 days before we got to the result, and the result was a tie. Right? From that time to today, wherein T20 is a 20 over match between two sides, usually takes between 3 to 4 hours. And as I said, this is huge. And the chart here shows the viewership that we had, which is 500 million people which were watching the last World Cup. And I've deliberately put this slide. It's not one of the matches. That happens in almost every T20 match. The reason why I put this was, this happened here, right here. It was the World Cup, last World Cup happened in United States and West Indies. So it's closer to where you are. But more importantly, India ended up winning that World Cup. And hence this 500 million is very, very important for us. So think of it. Fans, it's almost like a second religion. Fans are looking at better ways to engage. And that's leading to this fantasy sports. So there are 490 million online game players. And a large portion of that, a substantial portion of that is on fantasy sports. And one such platform is Dream11. Srijan, why don't you talk about that?
Thank you, Satinder. So, any of you who have recently followed the Cricket World Cup that has happened, you must recognize us from the jersey. This World Cup was very special to us because we won it after so many years. And this is a nice picture of our Team India jersey, women's team and men's team, and a nice picture of our jersey in Times Square. So who are we? We are world's largest fantasy sports platform. How large? How many users? Satinder just mentioned that there are 500 million cricket fans. How many users out of those do you think Dream11 has? Can you guess? 100 million, 150 million? So we have more than 220 million users. How many users do you think we added in just last year? 10 million, 20 million? So we added more than 55 million users last year alone. To put it in perspective, it is 15% of US population. How many concurrent users do you think we had, like number of users playing the app together at the same time live? 1 million, 2 million, 3 million. So our peak concurrency is 15 million users on the app live playing the game. And how many concurrent requests do you think these users produced? So 376 million is the number of requests that we got this year in IPL. IPL is Indian Premier League on our API gateways. So this is something that we'll talk about today, these two numbers, the concurrency and the number of concurrent requests. But before that, let me take you through a typical fantasy match journey. We usually have multiple of these matches running on our platform in parallel, but we'll focus on one today. So what we do is we typically open a list of contests that we serve for a match 2 to 3 days before the match start time. And this is when fans start coming to our app and start joining the contest that we are hosting for them. And just before 30 minutes of match start time, there is something called toss in cricket, where you decide who will bowl and who will bat first, similar to toss in other sports. And in these 30 minutes, a lot of users come and engage with us. Almost 70% of the fans join in this period. Then match starts, and a T20 match, as he said, is approximately 3 to 4 hours, and this is when users come to our platform to check their ranks, points, and we continuously update our leaderboard, and we try to do it as fast as we can. And like in cricket, every match ball is 5 to 10 seconds, so we have to update the ranks and points of our people, of our users every few seconds. And then when match ends, we declare the winners and users come to our platform to see their rewards. But what is the user traffic pattern in this timeline? So this is our traffic pattern. This is the graph of user concurrency. Specifically focusing in these 30 minutes, you can see something very strange starts to happen when there is toss. What is happening here? In our line of business, when lineups are announced at the toss, when we know exactly who are the players who are going to play in this match, that is when the excitement starts to begin. That is when the commentary is happening on the TV, there is analysis, everyone starts to coming and start seeing the match on the TV, and a lot of users start coming in our platform. There's surge of traffic that we get. And once the match starts, then continuously users start to engage with the app to see their points and ranks. Now I'll hand over to Satinder to talk about how AWS helps us.
Thank you, Srijan. That was a massive scale, and the concurrency is pretty high and in a short period of time. That introduces a lot of challenges. And I'm talking about the top 3, and then hand it over to Srijan and Rachita to detail them further. The first one is just the scale. On a peak match day, and the kind of thing that Srijan showed, there are almost 46,000 EC2 instances that are running. 90% of them are spot instances. There are 163 application load balancers that serve more than 145 million requests per minute. And when you combine these two factors, there are unique challenges that come. When such large number of instances are coming, then you need to find a right balance between doing detailed health checks versus superficial health checks. You need to find the right balance and the right mixture. And then it percolates to databases as well. There are over 166 Aurora MySQL instances, and one cluster, which is the largest cluster, does around 1 million requests per minute, a single cluster. And there are 166 clusters. Last but not the least, given the traffic that we are talking about, nothing is complete without caching. So there are over 50 Elasticache clusters that support more than 4 million requests per minute on a single cluster at peak. The second consideration that I wanted to talk about is cost. Given that 90% of instances are spot, we need to find the right balance between ensuring availability of spot instances as well as cost. And over a period of time, we have experimented with various allocation strategies, and we have finally zeroed down to capacity optimized as the most optimum one. Very recently, we have also started experiment with price capacity optimized, and we're seeing encouraging results, and we're thinking through whether that can be a default strategy. Right now, there is a combination of capacity optimized and price capacity optimized. Currently, we have over 140 type of instances in spot fleets that are listed, and we are also experimenting with using attribute-based selection just to see whether that will be a more effective use. The point being that you have to have large number of instances, and finding the right balance between cost and instance availability is foundational to this scale. The third one is security. Now, when you're into fantasy sports and such large number of scale, it becomes very, very important that you differentiate between what a genuine traffic would be and what a malicious traffic would be. Right? So there are two things that we have done. First one is the defense in depth approach, starting from a very comprehensive security posture, which consists of right kind of a governance, to Amazon Inspector for vulnerability assessment, guard duty for threat management platform, and more importantly, web application firewall, to ensure that the malicious traffic can be blocked. But again, thinking about the scale introduces new challenges. And one of the challenges is that when a peak traffic comes, then usually this traffic would be originated from mobile devices, which are leveraging ISPs, which means that our capability to identify what a bad IP versus a good IP is fairly limited, because a DDoS attack may be launched through mobile devices which are leveraging an ISP to connect. So we built a lot of automation, and this is one example of it, wherein we are able to detect in real time the kind of bad requests and take actions so that we are able to, for a temporary period, block an IP address in case we see multiple kind of inadvertent requests coming from that specific IP, only for a short period of time. And using this technology, we are able to block hundreds and millions of malicious requests every day. Scale, cost, and security are foundational. To address some of the other engineering challenges, let me hand it back to Srijan. Srijan, over to you.
Thank you. So now I'll talk about few of the key challenges architecturally that we have and how we solve them. First one is impulse traffic. This is the traffic that I showed you in these last 30 minutes of the match start. The second one is updating the leaderboard constantly in real time to keep up with cricket, so our users have the best user experience. Third one is dealing with failures at scale. And fourth one is personalizing the matches that users see on the app in real time. So focusing on the first problem, this is an actual snapshot of requests per minute on 26th of May, and this is for IPL final. IPL is Indian Premier League. This is one of the marquee cricket tournaments, and it is equivalent to Super Bowl here. So at around 7:02, you can see when lineups are announced, this is the inflection point where we start seeing a surge of requests, and you can see from 60 million requests per minute to 270 million requests per minute in just 3 minutes. And you can imagine then none of this auto scaling can work for this type of surge. And hence, we recognize the need to be able to predict our scale beforehand and then scale our systems to be able to serve the users that we are going to get in next few minutes. Hence, we decided to create a system called Scaler. As the name suggests, this is a system which is used to scale our systems appropriately for the traffic that we are going to get. It specifically does two jobs. One is predicting the traffic that we are going to get in next 15 to 30 minutes. And second, scale in our system just in time to do that. So I'll talk about the architecture and about these two things that it is doing, predicting the traffic, focusing on the first one. So this is our prediction flow. What we have done is we have trained a model using a lot of historical data of past years of seeing our traffic based on the supply that we have. So the type of match we have, the number of users that we have, DAU, their pattern of joining the contest on that day. We have trained the model using all of these data points, and then model understand if there is going to be this type of match and this is the DAU these days, and this is the joining pattern of today, then this should be the traffic at this time. And it fairly predicts for next 15 to 30 minutes. Then this model continuously do this prediction and then start putting this to a S3 bucket where we have triggered, we have put a Lambda which gets triggered and is consumed by a consumer to be put into a Aurora database to store this information where it is ready to be consumed by upstream systems. The next flow is actually to be able to use this prediction of concurrency data to actually scale the systems for the users that are going to come in next 15 to 30 minutes. So what we do is we continuously run a scheduler that reads from this Aurora database, and if it detects that it is going to be more users that are going to come in next 15 to 30 minutes, then it tries and calculates the requests per minute that will come to all the systems that we have, and we have more than 200 microservices. So the request that each system will get will be different. So we try and calculate that based on the predicted concurrency that we have, and then we ask our core engine to be able to talk to AWS APIs to tell AWS APIs and ASGs to actually scale the system for the traffic that we are going to get. We are proud to say that we have been using this system for last 2 years. It is the de facto system for us for automating the operations. We have scaled ASGs more than 16 million times, like that is 750,000 per month. And more importantly, we were able to save a lot of developer time in operations with this and make them happy. Like more than 100K hours of developer time has been saved with this. So what is next? As Scalar is a very household name for our developers, and we want to build more features to make their lives even better. So what we are bringing in is ability to be able to react to arbitrary events like push notifications or match delays due to either player injury or rains or other things, because these are the events which will actually affect the predictions that we have done and might not incorporate for these arbitrary things. So we need to be able to react to these things. Second one is provide a rule-based engine so that every developer can put in their rule to calculate the capacity that they require for a particular prediction, because no two systems are same and it is difficult and it might require custom logic to calculate what capacity do you require. And third one is adding support for other data stores like DynamoDB, Aurora, EMR also, so that we can leverage the system to decrease the operation time in these things also for our developers. So the next problem that I'll focus on, next challenge that I'll focus on is real-time leaderboard. And ranking specifically 20 million teams every few seconds, because as I said in cricket, every match ball is 5 to 10 seconds, and you have to keep on updating the points and ranks of the users that are playing on that contest as the match is going to progress in real life. Here is the image and GIF of a leaderboard that we are updating every few seconds. You can just glance on it, understand what is happening. So before getting into what exactly is the challenge and how we solve it, let's understand the broad architecture that we have. So first we have a team service where data of all the teams that have been created for this match by our users are stored. Then there is contest service where all the data of the contest that users have joined for this match is stored. What we do is as soon as match starts, you are not allowed to edit teams or join any more contests. So we log this data and dump this data as a one-time activity to one of the S3 buckets. And then we have a service called Fantasy Point Service. This service is basically responsible to understand the real-life match event. So let's say there is a match which is Australia versus India, and somebody's bowling, somebody's batting. So this service is basically picking the events from a real-life match and calculating and converting those things into actual points to every player that you'll have. And then it goes to a Kafka, which is subscribed by our Spark streaming cluster where all the magic is happening. This Spark streaming cluster also have the data that we stored in S3. This big Spark streaming cluster is continuously subscribed to taking the event, doing the processing, computation, and then writing it to leaderboard service to serve our users to show them the leaderboard that I show in the last slide. So now let's understand what is the data size, what is the quantum of the problem we are dealing with. So in a typical IPL match, we have contests, more than 1 million contests that we run for our users, ranging from 2-member contests where 2 players are playing with each other to 20 million members where there's a big contest and 20 million people have created unique teams. The contest team data size for this match will be approximately 200 gigabytes. And mega contest alone, which is of 20 million spots that I mentioned above, is alone of 80 gigs. And to put it in perspective, a fairly large machine, which is M58 large, has the RAM of 128 gigabytes. So specifically focusing on the mega contest, what are these problems? The first one being out of memory issues. So often at times we have seen the executor, the Spark executor where the mega contest lies, have just enough memory to be able to do its work. And because of either GC delays or a parallel match competition running on the same executor, we have seen it doesn't have enough memory to process, and then you have to redo the iteration again, and our users will have bad user experience for that period of time because the points are not getting updated for those many balls. The second one is scaling the cluster, whole cluster. So as the mega contest again can lie on any of the executor nodes, then you will have to scale up all the nodes of the cluster, and hence you'll incur a lot of cost. And third one is we are not able to leverage the parallelism as much because again, the mega contest, wherever it will lie, that executor will have to do a lot of work because it is going to sort 20 million rows by itself, whereas other executors are only sorting for smaller contests. So they do their job faster than this executor, and this becomes the bottleneck. So how do we solve it? We solved it using good old technique called salting. We use salting to break down the mega contest or the bigger contest that we have into smaller chunks. And I'll explain the stages of what is happening in Spark streaming now. It is little too technical, but try and follow me. So this is stage 1. In stage 1, we have data in all the partitions. So in partition 1, we have data of contest 1 as well as contest 2. In partition 2, we have contest 1, contest 2, and contest 4, and so on and so forth. So as a first step, using salting, we introduce a new column called salt key and break down the bigger contest. Let's say in this case, C1 is the mega contest. We break it down into multiple chunks. And now you can see in the stage 2, we have C1 broken down into C1 underscore 1, C1 underscore 2, and so on and so forth. Now as a next step, what we do is we repartition all this data. We do shuffling of this data and repartition it using the salt key as group by. And now you can see in partition 1 for C1_1, all the rows exist here only. And similarly in partition 2, C1_2, and so on and so forth. So what has happened is the bigger contest has also been now divided into multiple small chunks. And what we have done is all the data, all the rows of that chunk now lies in just one partition. So now it's easier to sort each partition for that contest, for that salt key, and this is what we do. Then we basically pick top 2000 spots from each of these partitions for each of the contests and merge sort them and put it in our leaderboard service to be served to our users. Why top 2000? Because we show top 2000 ranks for each contest on our app, and these top 2000 rows can lie in any of the partitions. So we have to pick top 2000 from each of the partition, merge sort them, and then write it in our leaderboard service continuously, do it every 10 seconds, every new event, and give our users the experience that we want to give them. I'm happy to say that with this, we were able to leverage as much as a lot of parallelization as we could. And we could reduce the computation time from minutes to seconds and give our users a real-time, very exciting experience that they can follow the cricket match live on TV as well as on the app. Now I'll hand over to my colleague Rachita to talk about other challenges that we have.
Thanks, Vijay. So we did see like what kind of challenges we face because of the tremendous scale that comes on our systems on a popular match day. But we all know that softwares are prone to failures. Whatever we do, whatever we prepare for, we should also have mechanisms to prevent these failures or handle them gracefully. Resilience is something that is part of our architecture philosophy, and we always like ensure that our systems are resilient enough to these failures, known and unknown. But why it's so important for us? The first reason that we have discussed enough is the excessive request. So we do have a lot of ways to predict, we do try our best, but still in certain situations we get much more than anticipated or expected. The second reason is we need quicker recovery mechanism. It's a 30-minute window. In these 30 minutes, we have to give the best of user experience to the end user, and it's also revenue critical period for us. So if something goes down, it needs to come back to its original state or the working state as soon as possible. The third reason is minimize impact. That in spite of doing whatever we have tried, the mechanisms for recovery, if they don't work, then how do we limit this impact so that only a small percentage or a subset of users are impacted because of failures and majority of users are able to enjoy, play, join contests on the platform. What I'll do next in the following slides is give examples of some of our critical services and systems where we have tried to address this, all the three reasons for resiliency in our architecture. We'll start with the excessive request part of it. So we saw like how we have an automated system that's scaling up all the applications well in time for the traffic to come in. But because of certain reasons, let's say we get more traffic than anticipated. This is what a simplified view of a system looks like. There's an API gateway, there's a service foo which talks to another service bar, and there's a data store that's for the bar service. But due to this excessive traffic, this data store is not adequately provisioned. The capacity is short. It gets overloaded. Or there might be certain slow queries that's causing it. Now the service bar is able to identify this and it says, I'm full. I'm at my max capacity. I cannot process any further request. It will start dropping these requests very gracefully. Now this service bar will in turn communicate to service foo. That also says, now I'm also full. I cannot take any further request. The gateway understands this and starts dropping the excessive request. This simple mechanism of back pressure, which is very core to reactive programming, helps us in situations where there is more than anticipated traffic and we need some time to react to it, to have some operator intervention to increase the capacity or the infra footprint. In those times, majority of the requests will continue to be fulfilled, only the excessive requests will be dropped here. The other mechanism that we have built throughout our ecosystems and mesh of services are circuit breakers. But why do we need circuit breakers? Because we have systems with different criticality. Circuit breakers, as the name suggests, whenever a requesting service feels that the latency or the threshold of errors is beyond its acceptable limit from the requesting service, it wants to safeguard itself. So let's say here, if the API gateway understands that service foo is having either very high latency or very high percentage of errors, it will open the circuit. The circuit breaks here for some time, and then after some time we try to reconnect and see if the downstream services have recovered. This is not only between our gateway and service, between two services, and in fact between our services and data store layer. So I'll later share an example where how this circuit breaker between the application and data store also helps us to maintain the system health and not the entire system goes down. So backpressure and circuit breakers are saviors for us. The second example that I mentioned, the reason was quick recovery. The best example that I can take is of a team service. Now what is team service? Users make fantasy teams on the platform, and that's core to our business. Users want to keep on modifying, editing, and choosing the best of the team till the last minute. Generally, that's a 30-minute window. But if there is a rain, or if this window shortens to as low as a 5-minute, pitch condition changes, match condition changes, the lineup will change, a lot of factors change. Users come back to the platform and want to edit it again. This service sees a throughput, a write throughput of as high as like 90K requests per second to 92K requests per second. To put it into perspective, largest cricket stadiums that we have a capacity of about 100K. So imagine everyone sitting in that stadium and deciding, I want to edit my team. And every edit needs to be saved. Otherwise, it's a breach of user trust. It's not a fair play. Now, this system is so critical that we need the right recovery mechanism. What we do here is, it's a very simplified view of our active-passive setup. We have an active data store, and these are Aerospike clusters. We do a dual async write to a passive data store. From the active, we have created a custom loop which keeps on filtering these active records and writing it to passive. At the same time, passive also has this loop for active. Why? Because at any moment, if there is an issue of capacity in the active, we are within seconds able to switch to passive. And when we switch to passive, there is no impact on user experience because all this data is present in the passive. And this loop is continuously running. We have performance tested the system for as high as 250K write throughputs. And we have also done a lot of chaos testing in a non-prod environments where we constantly keep on replicating these scenarios to ensure that this recovery mechanism works. And also production drills to ensure that this active to passive switch is happening within those few seconds as well as there's no data loss. Why we don't rely on the XDR mechanisms or there is also a async write that's happening? Because we want to be double sure, 100% sure that there is no data delay between active and passive and there's no data loss. Because if there's anything that a user claims that my team was not saved, I was not able to edit the team, for us it's a bad user experience and we might have to give up the entire money back to the users for all the rounds and contests. So this is a quick recovery mechanism that works beautifully for us, and especially in those times when we get those unexpected traffic or in crunch situations. The third thing that we talked about, that give or take, we have designed some great systems, but things go wrong. Then how do we minimize the impact? So the example I would like to take here is of our wallet service. Wallet, as the name suggests, is a ledger. It's where the account balance of users are maintained. All the transactions of money in, money out, every single penny comes to this system. So users are trying to deposit money to play more contests on the system. Some users are trying to join contests with the money that they have in their account balances. There are a lot of other smaller purchases happening on the platform. And apart from that, let's say if something happens around or a match is abandoned, then we would be processing back that money also in the wallet so that users can play the next contest with that money. So in short, a lot of right transactions are constantly happening. Now, at a very high throughput, what happens is we need a performance that's not served by a single cluster. We see writes as high as 13 to 14,000 transactions per second per cluster. Overall, including the balance checks, because it is an atomic system, you need to have the balance to deduct the money. So every calling system or a client even checks if there's a balance available or not. The total RPM goes as high as like 135K. What we have done is we have sharded our data store layer. And we have something called a shard meta that is aware of which user information or which user's account balance is present in which shard. So the wallet service talks to this, quickly gets the information on which shard this transaction is to be performed, and from the multiple shards, the transaction is executed. So that's why the account balance is always same, intact, and we are able to manage the high throughput. But that's on the performance impact part. Now, I'm not sure how many of you watch IPL games, but IPL games also happen back to back. So there is one game, that a 3-hour game that would be ending, and another popular one would be starting. And this is a period of overlap. What that means is that users will be doing all these actions of deposits, joins in that 30-minute window, and the previous match would have just ended, and the match ends, we identify the winners. Now, what do winners get? They get rewards. What are the rewards? It's the money. So these winnings start getting credited in these user accounts. And as like users, we want instant gratification. So it's not like you will get this money after 5 to 7 working days. It is instant. The moment you win, you get this money in your account balances. What this means is there's another system of winner dispersal that's running in parallel and starts dispersing money at a very high throughput. So it's double the throughput on the system. Throughput is still okay because we have the capacity, we can scale horizontally, we can scale vertically. But the challenge here is it's a wallet, it's an account balance. It's a single tuple, it's a single value for a same user that needs to be constantly updated, credit, debit. In certain situations, let's say the same user is getting the money, also trying to join contests, and on certain pocket of users where in a particular shard, we start observing latencies or certain capacity issues. What we do is, because I talked about those circuit breakers, our application is aware about it, and we just break the circuit from this particular shard. So what has happened here is, let's say there are 10 shards, 90% of the users are unimpacted. They are able to continue their BAU, joining contests, playing on the platform, and they are not impacted. The blast radius has reduced to just those set of users for that time duration in which this particular shard needs to recover, or we need to quickly upgrade it to a larger capacity cluster. So that's how sharding has helped us have a reduced impact in case of an adverse situation when things go haywire. So these were the things, and this is how we have addressed for resiliency in our systems. Next, I would like to talk about the fourth challenge that Srijan mentioned was around personalization. We all use a lot of online products, e-commerce website, a lot of other games. Personalization today is the key. And definitely we also want to give these 220 million plus users their personalized experience because the personas vary a lot. It's a large user base. We personalize the matches that the user can play, the recommendations, the contest in each matches, their payment journeys, their discounts. But one particular example that stands out for us is the match personalization because it's the first step that's happening on our homepage of the app where every user is coming. And we do it in almost real time for 15 million plus users. Couple of years back, we were not at that stage. And we had these challenges. The first challenge was evolving user preferences. Because it's a large user base, users change their preferences of sports they want to play for, or the teams that they love, or the players for the playing teams, or the tournament format itself. Like a new tournament comes up that gains popularity. So these are ever-evolving user preferences that we need to cater to and care for. Otherwise, the personalization won't be efficient and effective. The second thing is relevancy is not recency for us. It's very easy to just sort out all the matches from the start time. So one match is ending, okay, this is the next match, this is the next match. But is it relevant for the user? Might not be the case. The third challenge that we used to face is batch predictions. So when we didn't have this almost real-time inference and recommendation system in place, we used to do recommendation in batches, but these become stale because a lot of matches are happening on the platform. In a day, we do like close to 150 to 200 matches on the platform. And if we do batch predictions, data becomes stale, and also it's not a cost-effective one. You are doing for all users because in the next 20-30 minutes, you don't know which users are coming on the platform and would need your recommendations. The fourth one here, the challenge being was heterogeneous compute. With Spark, we were not able to do this, and if you look at our diversification strategy, we believe in that because overall we want to leverage as much infra available and at the least cost possible. So how did we solve for these challenges and achieve what we have today? We built an in-house system that we call Darwin that personalizes at scale. Now it's a very simplified system if you look at it. What we use as the base is the Racer. For those of you who are not aware, is a library for models where you can build online inference APIs and you can run machine learning models and applications on top of it. So why did we choose Racer? And also we use a very customized version of Racer Lite, and we have done a lot of modifications to manage the kind of throughput and latencies that we expect. On top of it, we have created a compute manager that is just optimizing for how these workloads will be distributed in the best efficient manner. It's a multi-tenant system so that a workload of recommendation of contest doesn't interfere with the workload of a match personalization. On top of it, all these models that our data science team builds runs. Feature store is there. Feature store contains the user information, their matches information, their past history, the user matches, user contests, all about the users that information we can use of. And on top of that, we use multiple use cases. Like in case of match personalization, there's a service that gives the default match information for this user, and we use this personalization engine at scale, run this particular model, and reorder for this user the desired recommendations. Using Ray, we are able to have latencies as low as 4 milliseconds, 1 billion inferences, And overall, the P99 for this entire system is as low as 50 milliseconds. And just to give a cost, because I talked a lot about like cost is an important factor here, it's just $150 a day at what we are able to achieve for this kind of scale. This is it. This thing is action. So if you see on the right-hand side, that's our home page where these match listings are coming, which are constantly getting like reordered based on the recommendations. This is the user request. So this is a default match order. We get the features from the feature store. We calculate, we put it on the platform of Darwin, the engine runs, we get the scores. Based on these scores, we reorder. And this is happening at each match join that is happening. With each match that you're joining, each contest that you're joining, this is getting refreshed. And that's how we are able to achieve this is almost real time. In fact, the next that we are exploring and experimenting is taking this personalization engine to the edge layer so that we are able to do it even lesser than 50 milliseconds. Because every millisecond counts for the kind of scale that we see and the kind of user experience the fantasy players want on the platform. So we have talked a lot about like what we are doing, how we have solved for architecture, but as a conclusion, what we would like to leave all of you with is what we are looking forward to. What we are looking forward to is, first thing, we are in a domain that's all about fantasy sports, and it's a very evolving domain. We already support 12 sports, but we want to constantly engage the users on the platform. And we want to support more and more formats, more and more sports. What it requires us today to do is a lot of like new development, a lot of new systems. So we are investing in building platform solutions for our business growth experiments. These will be very specific to maybe fantasy or the domain that we are. But building these platforms will help us take new features, new formats much faster to the end user, to test them, to see if it is a good PMF, and then enhance them further. The second thing that we constantly look forward is more concurrency. Yeah, 15 million is a lot. If we compare to a lot of other online popular games, they don't see this number as a concurrent user. Maybe this number is more as a DAO, and that too spread across the globe. But for us, this is going to be higher. IPL 25, which starts in March, will be higher. And that constantly pushes us to see what are our breakpoints, where are the single point of failures, how do we do better at identifying them and changing our architecture designs. The third thing that we are now aggressively looking for is, for us, managing multi-sharded data stores is constantly becoming an operational overhead. It's a lot of dev effort. We have built a lot of tooling, platforms, and we have tried to integrate with our scaler system. But data store, scale up, scale down is not that seamless a process, and especially when you have a lot of transactional systems. So we are looking at things like Aurora Limitless, DynamoDB, so see if we can reduce it to as low as 70% of what we do today. And last but not the least, AI/ML is something that everyone is exploring. It's all over the place. A lot of use cases are there which are being explored on the product Dream 11, which is for the end user, which is in terms of customer service or giving them a lot of assistance, AI coach and all. But this one particular thing is something we as a technology team is investing on. For us, quality to the end user is very important. And we are investing and exploring ways of how we can leverage AI/ML to automatically generate test cases and cohesive synthetic data, because that's a major challenge for us. When you have 200 plus services, you have like thousands of user flows where you need integrated cohesive data. So this is what all of us are looking forward to solve for in the next year. We hope this session was useful and all of you had some of the other key takeaway, and we have some time left for Q&A. So thank you everyone for your time, and we'll open it up for some questions and answers.